Hi there and welcome to this video for Senior Physics on Nuclear Physics. In this video we're going to explore how we can detect nuclear radiation and the devices that we utilised as time progressed for looking at how radiation actually existed. Now the first discovery, as we know, came in 1896 with Enric Becker, and he was studying the rock which ended up being uranium, and what he was doing was taking the uranium and he was taking a photoplate. Now the photoplate was just a normal photographic glass plate which he was wrapping in paper, and he was placing the rock on top of the paper and he was placing that whole apparatus in the sunlight. Now he was working on the principle that the sunlight was causing the rock to emit some substance, and what he was getting was this shadow which is generated on the plate when he developed the plate, and you can see that shadow on the top right hand corner of your screen. Now what he didn't realize was that what was being emitted from the rock was this radiation. Now it wasn't until he had a rainy day and he actually took a sample of the rock and a photoplate all set up, and because there was no sunlight he decided not to place it in the sun. He put it in a drawer and went off for the weekend, came back, and for some unknown reason he developed the plate. And when he developed the plate, he noticed that same shadow was present. As a result, he determined that it had nothing to do with the sunlight. There was something inside that rock which is actually causing this shadow on the photo plate. What it ended up being was this idea of radiation. And you can see down in the bottom right hand corner there, we've got this idea of this uranium which is stuck on top of the photoplate in the dark, and it's emitting these alpha particles. These alpha particles are then reacting with the photoplate and as a result generating the image that we can see. So that was one of the first discoveries behind detecting the presence of radiation in our natural surroundings. Later on, fluorescence was used with Ernest Rutherford. Now, Ernest Rutherford basically worked on the ionizing properties of this radiation. And when this radiation ionizes certain substances like zinc sulfide, diamond, barium, platinum cyanide, what we get is these flashes, this production of light. And by counting the amount of flashes that you get will determine the number of, or the radioactivity which is present from the particle. More flashes, more radioactive that particle happens to be. Now this was very, very tedious because it consisted of looking down a microscope and looking for these individual flashes and counting them. And you can imagine as time goes on you get tired, it's very, very inaccurate. But it wasn't until later on in the 1940s that a photomultiplier was introduced, which actually allowed the ability to detect each of these flashes and then use some simple electronics to count those number of flashes per time. And then that was related obviously to the radioactivity of the substance. So here I've been able to pick up a little animation which shows that we've got the radiation which is generated here. That radiation causes, if you can see just in here, we get that ionization. Ionization then generates that light. That light is then converted into an electrical signal through the photomultiplier, and then it's taken out and counted as an electrical signal using some fancy electronics. We're not going to go into that in any great detail. These are the sorts of things that you may use if you're going to university and you happen to do any radiation work. You'll use this scintillation counter, and literally all it will have is a dial, and it will be telling you how many flashes you're getting per second, and that will then be linked to the activity of that radiation sample. So what else was there? Was that there was the electroscope, which was used by the Curies. Now Marie Curie basically looked at the fluorescent salts and used the concept again of this ionizing radiation. Now what they did was they took an electroscope and they charged up the foil, and you can see in the diagram in the bottom right hand corner we've got a representation of the foil, and you can see the foil is negatively charged, and as a result it repels from the main shaft. Now what she then did was pass the ionizing radiation, and what the ionizing radiation did was ionize the air. So as it ionizes the air, we get these positive particles which are generated because we're knocking off these electrons. So if these electrons are being knocked off into the atmosphere, we can then get these charged ions, which will then be attracted to the negative electroscope. Now, the faster the, as the positive particles hit onto the electroscope, what happens is the negative charges then move towards the positive ions at the top. The result is the leaf will begin to drop down. Now, if you can measure the time it takes for that leaf to drop down, you've got an idea of the radioactivity which is going on. Because remember, the radioactivity is what's ionizing the air. By ionizing the air, the faster or the more ionizing ability that radioactive particle has, the more positive particles are going to be generated, the quicker the negative charges on the electroscope are going to move to those positive charges on the plate, the quicker the leaf is going to go down. So as a result, they were able to work out this rate of collapse of the leaf based on the ionizing ability of the radioactive sample. And as a result, that allowed us to work out, if you take various different samples, you can then work out with time the radioactivity and the time and how the type of particles which are going to be generated. Now, from there, we then moved on to the Geiger-Muller tube. Now, we all know about the Geiger-Muller tube. That's basically a tube, and probably what most people understand is it's a tube linked to a box and it clicks. And the more it clicks, the more radioactive the sample is. But what actually happens is it again uses this ionizing ability of the radioactive particle. And you can calibrate the Geiger-Muller tube to detect specific types of radioactive samples. And obviously, the more ionization that happens within the tube, the more an electrical current is going to flow. And again, it's counting the number of charges which are generated as it flows through the tube. Now, that's a very, very simplistic version of the tube, because we're not going to go into this in any great detail, but what I've found on YouTube is a really good video, and I've linked it to this post, and it explains in detail exactly how the Geiger-Muller tube goes. And I'm going to allow the narrator in that video to explain the Geiger-Muller tube better, because he understands it a lot better than I have, and there's some really nice animation in there. So do click onto that post and check out how a Geiger-Muller tube works. Now, the final way of looking at the presence of radiation is using a cloud chamber. Now, again, I've put this up on the post on YouTube so that you can have a look at it. But what this does is it's the generation of the ionizing ability in a closed environment, and it's normally a cold environment. These cloud chambers are normally stored under dry ice, produces this cold environment, and we were able to pick up the radiation particles being generated. So basically, if I just switch it on, each of these white areas are liberation of radioactive particles which are going on within the actual chamber. So it's the radiation being emitted, and then what we're seeing is these particles coming off. And really what we've got, it's like watching a rocket go off, and we're looking at the path of these radioactive particles as they fly through the container. And obviously, if you do it in the dark, they're giving off light as well due to that ionization, which we talked about earlier. It's really, really cool to look at. And if you go onto YouTube, there's loads and loads of little videos which are cool to watch, and they're quite magnificent. There's also a great YouTube which I put on the post of how to make your own cloud chamber in the classroom. So do have a watch of that, and if you can get dry ice, then that's really, really useful. Okay, well, I hope you found that useful in that just running through the various different types of ways of detecting radiation. Most of the things that we're going to be using will be the Geiger Muller tube, and I plan to put up a practical in the lab using the Geiger Muller tube and showing you the various radiation that is emitted from specific types of particles. Okay, well, I hope you found that useful, and I look forward to you joining me again. Bye for now.